This is the video for toll gate dynamic programming routine. The routine starts over here on the left and finishes up over here on the right. The first thing it does is it fills numerically the 96 values at best cost with a high value, indicating that it hasn't found the best cost yet. Then it says move numerically the 8 values at gate cost to the best cost. So best cost is going to start out with just the cost of the gate, but it also needs to know the cost of moving over from the start position to that gate. So we're going to go around a loop to add the cost of moving. We set J equal to 1 move cost. Then we go around the loop for I of 0 to 7, one at a time. We're going to look at each one of those gates in the first row, and we're going to add to the first one 1 move cost. Then we're going to increase J by a move cost, and then the next time we go around there'll be 2 move costs. In other words, each of those first gates is a move away from the starting position. So after this is done, the first 8 gates have their best cost. Next it says for I of 0, and I doesn't end to all the way over here. The I is 87, 8 at a time. It's going to go around then for each of the 11 other rows of gates. And 8 at a time because there are 8 gates in a row. Well, the next thing it says, set M to I, then add 7 to it. Well, that's going to give it the offsets for the previous row of gates. Remember, we know the previous row is the first row here. Then it'll be the second row, third row, fourth row as it goes around here. So this is going to be used for the previous cost from I to M. Then it's going to have values A to B, sets A to I, but then it adds 8 to it, so its index is pointing to the following row. Sets B to A and then adds 7 to B, that's the end of the following row. So if it goes from offset A to B, that's actually the new row we're going to calculate the best cost for. Next, we set R to 0. That's going to have to do with the move cost. We then say for J of I, and down here we have next JM, one at a time. It's going to go around for all the previous best costs. And each time it goes to another one, it's going to have a subtraction down here for that value of R, subtracting the move cost. And we'll see that it moves one way, the move costs change, and it moves the other way, the move cost changes back. Alright, so now we're going around that loop for all the previous costs. And here we set S equal to R, that first move cost. Then we say set T to the best cost J offset. That's the previous row's best cost for that position. Then we say for K of A, down here to K of B, well, that's our new row's offsets. We're going to go around this loop for each one of the gates in the new row. We set U equal to S. Then we take the absolute value of U, because U is going to have this negative value plus a positive value. We need to know the difference between the position that we're working on and the position, well, to say the position for the previous gate and the position of the gate we're having in the new row, what is the cost of moving between them? That's going to be in the value of U. And the absolute value is taken because it could be negative moving this way and positive moving that way, but we want to know the positive difference. Well, then we add T, which was the best cost we have for the previous gate, the cost of moving over to this new gate. Then we say if U is greater than or equal to a cost we already found for the new row, We don't want to do it because it's no better than what we have. We go to BA, and as we go around this loop, we add to the move cost. So each time we go around here, we're choosing the best cost that we can get coming from this particular gate of a previous row to this gate in the new row. And each time, if it is a better one, it sets the best cost for getting to that gate to U, and it has to remember the way back. It has to say, well, the best index then at K is J. Remember, in dynamic programming, we're solving little problems. This is a little problem we're solving, but the big problem solution is only determined by us knowing how to get back to the beginning when we find the best cost for the gates at the end. This is how we find our way back. But once this is done, we finished the cost of moving to that gate. But then we have to do KA to be here to add the cost of that gate to that best moving cost we had. So here we're going to go around, and all the new gates that we did, we're going to add the gate's cost to what we just figured out was the best moving cost down here. So that's the total cost of getting to that particular gate. Well, once we've gone around here the 11 times to do the other rows, we then can proceed on to find the answer. We set the last cost, the large value. We set the last index to 0. We set T to the move cost. We multiply T by 8. Well, when we do the find the answer now of the cost of the gates and then moving all the way to the right to the end. Well, the first one on the left is going to have to be 8 times the moving cost. It has to move 8 times to get over. So this value of T is that, and we'll see as we go around this loop, it's going to subtract from that because we get one move cost closer to the end. Well, it sets S to the best cost of I, and here it's on the last row because it started with I of 88, and it's going to go to 95. That's the last one. It's on the last row. These are the offsets for the last row. It gets that value, adds to it the cost of moving to the end, and then it says, is that greater than or equal to the last cost we already have? No. If it's not better, we go down to BC and we don't remember it. But if it is better, we set our last cost to that value of S, and we want to remember the index of where it was. So this is doing the moving over to the end, adding the move cost for that. Next, it sets J equal to that last index, the best one it found. It sets K to 11, and then for I of 1, down here to 12, it's going to go around and find all the best answers. That is when we're moving backwards through the gates. Remember over here, we told it to remember the previous gate each time. Well, now we're going to go backwards through it and find them. So we set L equal to the best index at J. Remember, first it's this last index. We modify it by 8. That's to do the modulus, so we get a value from 0 to 7. Then we set the trail sub K to that value. It's telling us which gate it is. Remember, over here we remembered its overall index, but not what row position it was. That's why we did the modulus here. We want to know the position from 0 to 7 it is from left to right. So remember that in trail. We set J to L, we subtract from K1, and we go around again. Each time it's pointing to the gate value in the previous, that gives us the previous best answer that we figured down here, and then it has the trail all the way back to the beginning of the minimum cost. Well, this is the video for the toll gate dynamic programming routine.